So in this video, we're gonna talk about the theories of acids and bases, and there's two of them. Um, so let's get into it. The theories of acids and bases kind of describe how you can identify something as an acid or a base chemically. So the first theory is called the Arrhenius, or the Arrhenius, or the Arrhenius, depending on what part of the world you are from. Um, and it basically is going to outline it's the most broad definition there is for acids, and this is how it reads. Okay, it says an Arrhenius acid is something that yields hydrogen ions, H plus, as the only positive ion in an aqueous solution. So a couple things to remember: aqueous solution means in water. Okay, H plus is also known as a proton, and hydronium, H plus, and proton can all be used synonymously. They all mean the exact same thing when it comes to acids and bases. Obviously, H3O and H plus are different, but they do describe an acid. They do, both are produced during acid formation in water. So, what I want to further elaborate on is anything that has an H plus and then donates or gives off an H plus in water is known as an acid. Let me get rid of this thing. There we go. So, for instance, if I took HCl, which is hydrochloric acid, so yes, it is an acid, and I put it into water, the products would be H plus and Cl minus. They break apart, they dissociate. This right here is the reason why we call HCl an acid. That's what it makes. By itself, in water, it donates, it gives this off. This is the acid ion. All right. Another way to write that, and it's the exact same formula. HCl and H2O make H3O plus and Cl minus. Now, these two equations show the same thing. They show a molecule being combined with water and ultimately giving off an ion that is defined as the ion making Arrhenius or Arrhenius acids. All right. I'm going to have this loaded, this presentation as well. So if you don't have time to write down the equations and you can pause it, or you could pause it, you can always look it up. So let's move on to the next part of the Arrhenius theory, and that's what makes an Arrhenius base. An Arrhenius base is defined as something that yields the hydroxide ion, the OH minus, as the only negative ion in an aqueous solution. So the moment something goes into water and OH is an ion produced, that makes it a base. An example would be NaOH, sodium hydroxide. Sodium hydroxide, in the presence of water, gives off a sodium ion. That doesn't make it the base, but this makes it the base. So a lot of the time when I'm referring to OH minus, I might say to you something like, what is the base ion? Or which ion makes it the base? Or if you look at the base ion, when I say those things, I'm talking about OH minus. And going back to what I was saying before, H plus will then be the acid ion, or H3O plus, or a proton. Any of those things would be defined as a acid ion to me. So basic general principle. H plus makes something an acid. OH minus makes something a base. So now, if you have your reference table, and if you don't, would be a great time for you to go pause the video and go get it. But I'm going to ask you a question. I'm going to ask you to pause once the question comes up. When you look at table K and table L, what do you notice about the molecules on each one respectively, as it pertains to what I just talked about with H pluses and OH minus? What you see is, for table K, things that look like this: HCl, H2SO4. Some people might be wondering why this OH is in that table. For starters, if you remember back to organic chemistry, the COOH group was called an organic acid. And I'll explain later on in the lessons why, even though there's an OH, it behaves like an acid. It doesn't give off an OH ion, it gives off just an H ion. But I'll go further into that later down the road. But the point is, what do you notice about table K? They all have H, and most of them just have H. And if you look at table L, you notice OH, OH, OH. There's also ammonium in there, or ammonia in there. I can't remember which one it is. Again, just like this, I'll explain why this is an organic acid. I'll explain why that one at the bottom of the table is considered a base. So table K and table L give you a nice reference of memorizing these definitions. The common acid tables has a lot of H's and just H's, just like acids give off just H's. And the table L bases, common bases, have OHs, just because bases give off OH. So it's a good little reference for you, so you don't really have to memorize it. But by the end of this unit, you'll know H is an acid and OH is a base. Now, this is always a funny topic of conversation when not this part, but so I always jump ahead of myself. So let's talk about water. Water is H2O. Is it acidic or is it basic? What do you think? Write it down. Think about it. Is water a little bit acidic? Is it a little bit basic? Does it burn your skin? Does it burn your internal organs? Does it feel slippery? The answer is it's neutral. I think a lot of you were thinking that. And neutral means that it has a pH of 7. It's right in the middle of the table. Now, the reason why something is neutral, such as water, is because if I took the H2O formula and I took the structure of the molecule, which looks like this, and then I rewrote H2O, HOH, what we actually see is that H2O gives off both an acid ion and a base ion. And when the H pluses and the OH minuses are balanced and equal, it's neither acidic or basic. It's this word called amphoteric. And that basically means it's both an acid and a base. It acts in both ways. It can give off either of those ions. So water's interesting in that way, I guess you could say. And then the last thing I have for this video is, this is the funny part. This is always a funny topic of conversation as far as the New York State Regents has turned into, and that is what we call the other acid and base theories, also known as the Bronsted-Lowry theory. So my mini spiel is that when taking a Regents exam, it used to be referred to as the Bronsted-Lowry which makes a lot of sense because the Bronsted-Lowry definition of acids and bases is the one that is used more universally because it's a more comprehensive definition than the Arrhenius. But the Regents likes to stick with the first theory more so than the current most up-to-date theory. And so the funny part of all of this is instead of referring to this by the scientists' names who this theory was named after, the Bronsted-Lowry theory, the Regents just refers to it as the other guys. The other people, the other thing, that we kind of use more often, but we just don't want to name it. Not really sure why that is the way it is, but here's what it means. And you're going to see it's going to have some very strong similarities, but then one blaring difference. And that is that acids are proton donors. I want to stop right there. Acids are proton donors. So just like before, a proton means H plus or H3O minus, the definition for acids is still the same. So whether we're talking about the Arrhenius theory or we're talking about the Bronsted-Lowry / the other theory, acids always give off H plus. Acids always give off H3O plus. Acids always give off protons. It's just that they call them donors. It's just a slight difference. The big difference is that bases are now proton acceptors. So it doesn't necessarily have to be in water for me to explain this. So here's an example. We have HCl and NH3. One is going to act as an acid and one is going to act as a base. One is going to give off an H plus. One is going to gain an H plus. Sorry. And so really what you have to do in situations like these is just connect the dots. So if something started out as HCl, did it become NH4 or did it become just Cl? And I'm assuming you all can say, oh, well, HCl became Cl because it lost H plus. And then I'm hoping that when you take the NH4, the NH3, and you go to the NH4, you can realize that change happened because there was an H plus gain. And so what this theory is saying is that if acids are proton donors, whatever loses an H is going to be the donor, making H plus H3O, HCl the acid because it went from HCl to Cl by losing a proton. Now that makes NH3, which goes from NH3 to NH4 plus, the base. Why? Because if from NH3 to NH4, there was a gain in protons, and that gain in proton is what made it a base. So those are the theories on acids and bases. There's only two of them. I'm going to post not only the Google Slides here, but I'm also going to post the note packet for you to either write in, copy down, or you can do it on a blank piece of paper. And then the next lesson will be some questions for you to kind of work through and try and figure out the fine details of how to determine if something is an acid and a base using table K, using table L, using the definitions of these theories. And then we'll work in a castle, and that's probably going to take us to the end of the week. So have a good week. Keep yourself out of harm's way, and I will talk to you soon.